Okay, so here I start lecture 2, which is on instrumented indentation technique, which is called IIT or depth sensing indentation. So this technique, instrumented indentation or depth sensing indentation technique, was proposed by W.C. Oliver and G.M. Farr in 1992. So according to this indentation technique, the hardness is defined as the applied force P over the projected area under load A. Remember, focus at the point which is projected area, whereas the hardness defined in lecture 1 was the residual area under load, and therefore the projected area under load A is measured from the indentation contact depth HC during loading. So therefore no imaging is required in instrumented indentation, and that is the advantage of instrumented indentation, because we do not have to monitor the process of indentation, and we do not need to capture the images of each indentation after each indentation is done. So this is the schematic of a depth sensing indenter. It mainly has 3 parts. The first one is the indenter, which is attached to a rigid column. The second part is the force actuator, which is used to apply the force, and the displacement sensor, which captures or measures the displacement of the indenter. So the force could be applied by electromagnetically using a coil and a magnet. It could also be applied using a parallel plate capacitor or a fixed plate capacitor. The force could be applied by using a piezo, whereas the displacement sensor senses the displacement, and these sensors could be capacitive or it could be LVDT. So this is the scheme of loading which we apply for depth sensing indentation, and the same scheme is essentially applied for uniaxial compression or tension also. So what we do, we apply a certain load for a certain duration of time, and after a certain amount of time the load reaches P max, and we hold that load for a certain amount of time, which is called the dwelling time, and then we unload that test specimen and reduce the load to 0. Now if we apply such scheme during uniaxial compression or tension, the load displacement graph is something like this. So initially the load varies linearly with the applied displacement, and when a certain load is reached, the behavior is no longer linear. It changes from linear to nonlinear behavior, and we call that the material is deforming plastically. Whereas in indentation we can obtain a load displacement graph which looks something like this, where with increasing load, increasing displacement, the load increases. On the other way, if we increase the load, the depth of penetration increases, and you can see at a certain point the slope of the pH graph changes, and this region initiates a elastic to plastic transition in the load displacement graph. Now if we increase the load until P max and then unload the material, the material follows this kind of unloading path. Now once we know that, we can use this pH graph to measure the hardness of a material and elastic modulus of the material. It turns out that the hardness and elastic modulus can be determined within plus minus 10% accuracy and sometimes better. So in figure B, I have shown the profile of an indenter. So the horizontal dotted line here, it shows the initial surface of the material. Now if we apply a certain load P, the indenter penetrates a maximum depth which is given by H. It is interesting to see that the indenter, which is shown by the inclined dotted line, it is not always in contact with the material. It is in contact with the material until a certain depth, which is called the contact depth and designated as HC. Now if we unload the indenter, the material recovers certain depth, and the residual depth is given by HF, which is the final depth, after unloading of the indenter. Now, if I plot that in a load displacement graph, we can see that with increasing load, the displacement actually increases, and when load reaches P max, the displacement is H max. Now, if we start unloading the indenter, after full unloading of the indenter, when load is 0, we can see that the residual depth is HF. And this unloading graph can be used to calculate the stiffness of the indent, which is defined as H equals to dP dH, means this is the slope of the unloading portion of the pH graph. Now, once we understand this pH graph, we can use that to calculate hardness by using this formula, which is P over A, where P is the applied load and A is the projected contact area at that load. And we can calculate the reduced modulus using square root of pi over twice beta multiplied by S over square root of A. So, this beta is a material constant and it could be obtained from data books. Now, it is important to note that both H, the hardness, and reduced modulus should be calculated if we know the projected contact area at that load. It turns out that the projected contact area is a function of the contact depth as defined previously. So, the formula is A is equals to 24.5 Hc square. So, what we want to do is when we make the indent, we want to measure this contact depth, and if we know the contact depth, we can easily calculate the projected contact area that can be used to calculate the hardness and reduced modulus. So, in the next slide, I would like to show how we calculate the contact area based on the contact depth, and that is called area function calibration. So, the goal is to find a material independent area function, which is A is equals to area function A, which is a function of contact depth. So, what we do, we take a material with known reduced modulus. We generally use a fused quartz, which has a reduced modulus of 69.6 GPa, and we make several indents on the fused quartz at various loads, starting from very low to very high loads. For example, in this figure you can see many pH graphs, and each pH graph is constructed at a fixed load. So, what we have one pH graph for each indent. Now, what we do, for each pH response, we calculate the contact depth Hc as from this relationship, which is H, which is the maximum depth, minus epsilon multiplied by P over S, where S is the stiffness and P is the applied load. The epsilon is also a material constant, which could be obtained from the indentation data books, and also the area under load A could be obtained from this relationship, which was shown in the previous slide. So, what turns out that we can calculate by plotting many pH responses starting from low load to high loads, we can calculate contact depth and the corresponding contact area from each pH response. And what we do, we plot those contact area as a function of contact depth for all those pH curves, and if we plot that, we get this kind of response, and this kind of response can be expressed in the form of a polynomial shown here, which shows A area, which is a function of contact depth, is equals to C naught Hc squared plus C1 Hc plus C2 Hc to the power half and other higher order terms. And the coefficient of these expressions, such as C0, C1, C2, etc., are given in the left hand side of the graph. It turns out that if we do higher load indents, that means at higher depths, that is at higher HCs, higher contact depths, the first term of this polynomial dominates the rest of the terms, and therefore, we can neglect this rest of the terms, and we say that area, which is a function of contact depth, is almost equals to 24.5 hc square, and this contact depth could be used, contact depth and contact area could be used to calculate the hardness and the reduced modulus by using the formula which were described in previous slides. Now, I would like to talk about some applications of the indentation technique. So, one of the application is strain mapping in the subsurface of an indent. So, what we want to do? We want to measure the plastic strain induced by a macro indent. So, in this figure, this triangle shows a macro indent or big indent which is loaded by a force P onto the surface of a specimen, and when we apply a certain load, it creates enormous plastic deformation in the subsurface below the surface, which is shown as a dotted line, and this region is called plastic zone. Now, to measure the plastic strain induced by this macro indent, what we need to do? We need to calculate or measure the strain at each point inside the plastic zone, and for that what we do? We perform a series of micro indents inside the plastic zone. So, once we perform the series of micro indents from the plastic zone, we can measure the hardness values from those micro Vickers indents. Okay? And then we can convert those hardness values to their respective yield strength by using sigma y is equals to h over 3. So, this relationship was discussed in the first lecture, and you can see that. So, we use this relationship to estimate the yield strength at each material point where those indents were made. Now, if we know sigma y at each point inside the plastic zone, we can measure the stress strain graph. We measure the strain corresponding to each sigma y from the uniaxial stress strain diagram. I will give one example here. So, this is the actual macro indent which was performed on the surface of a material, and that macro indent caused enormous amount of plasticity in the subsurface of the material. So, this region, this entire region is the deformed region, and what we have done a series of micro indents in this region. So, what we have done at a fixed depth, we have done indents along the width of the deformed region, and we have repeated that method at various depths. And after we perform these indents, we measure the hardness values, and those hardness values are plotted in this graph. So, only half portion of the indent is shown here, and you can see that the hardness values are greater in the regions which are close to the macro indent. The more farther we go from the indent, we can see that the hardness values reduce. In the next step, we convert those hardness values at each point to their corresponding yield strength by using sigma y equals to h over 3. So, these yield strengths are nothing but the von Mises stresses at each point inside the plastically deformed region. Now, if we have the uniaxial stress strain graph of the undeformed material, we can find out the strain induced at every point if I know the if we know the yield strength at each point where the indents were measured. So, if I measure an indent at certain point, we know the sigma y for that indent, and we know the corresponding strain associated with that indent. So, this is the way we can map the strain distribution beneath the macro indent, and this method is called strain mapping. So, here I finish my lecture 2, and in lecture 3 I will talk about a more advanced concept called size effect in a material. Thank you.